Welcome back. In Chapter 1, we explore working with real numbers. So far, we have covered sets and expressions in Section 1.1 and examined the structure of the real number system in Section 1.2. Now, it's time to transition to our next critical topic. Today, we dive deeply into Section 1.3, focusing on exponents, roots, and fractions. We will master how powers scale numbers, how radicals unlock roots, and how fractions partition values. Let's get started. A power is a multiplication in which all the factors are the same. For example, m squared equals m times m, and m cubed equals m times m times m. In this expression, m is called the base, and the number above is called the exponent. Imagine Santa Claus multiplying his magic gift boxes. If he doubles them at each house, 2 squared becomes 4, and 2 cubed rapidly scales to 8. That is the explosive speed of repeated multiplications. Let's mathematically derive the multiplication of exponents. When we multiply m squared by m cubed, we expand them into repeated factors. M squared is m times m, and m cubed is m times m times m. Count them all together, and we get m multiplied 5 times, which equals m to the 5th power. Thus, when multiplying powers with the same base, we simply add the exponents. Next, let's explore division. Consider m to the 5th power divided by m squared. We can write this as a fraction, with 5 m's multiplied in the numerator and 2 m's multiplied in the denominator. By canceling out 2 matching factors from both top and bottom, we are left with exactly 3 m's. This gives us m cubed. Therefore, for division, we subtract the exponents. Now, let's test your understanding with a practice problem. Simplify the following expression, m to the 4th power, multiplied by m cubed, and then divided by m squared. Think about which rules to apply first. Let's solve this step by step. First, look at the numerator. According to the product rule, m to the 4th times m cubed equals m to the 4 plus 3 power, which simplifies to m to the 7th power. Next, we apply the quotient rule for the division. M to the 7th divided by m squared equals m to the 7 minus 2 power. This gives us our final simplified answer, m to the 5th power. Rule number 3. When you raise a power to a power, you multiply the exponents. For example, let's take m cubed and square the entire expression. This means we multiply m cubed by itself. By expanding each term, we get m times m, multiplied by another m times m. Count them up, and we get m multiplied 6 times, which is m to the 6th power. We can find this directly by multiplying the exponents 3 and 2. Rule number 4. Raising a product or quotient to a power is the same as raising each of its individual elements to that power. For example, let's look at the product m times b raised to the 3rd power. This expands to mb times mb times mb. By grouping the like terms together, we get m times m, multiplied by b times b times b. This simplifies neatly to m cubed, b cubed. The same logic applies to fractions, distributing the exponent to both top and bottom. Let's check your skills with a challenging practice problem. Simplify the following expression. Inside the parentheses, m squared times b squared, and raise the entire expression to the 3rd power. Think about how to distribute the exponent to each element inside. Let's break this down step by step. First, according to the product to a power rule, we must distribute the outside exponent 3 to both individual elements inside the parentheses. This gives us m squared raised to the third power, multiplied by b squared raised to the third power. Next, we apply the power to a power rule. For m, we multiply the exponents 2 and 3, resulting in m to the sixth. For b, we also multiply 2 and 3, resulting in b to the sixth. Our final simplified answer is m to the sixth power times b to the sixth power. Rule number 5. Let's understand why any non-zero number raised to the power of 0 equals 1. Using the product rule, we know that m to the power of a multiplied by m to the power of 0 equals m to the power of a plus 0. Since a plus 0 is just a, the result is simply m to the power of a. Notice that multiplying by m to the power of 0 did not change the original value at all. Therefore, m to the power of 0 must equal 1. Rule number 6. Now, let's make sense of a negative exponent. Consider m to the power of a multiplied by m to the power of negative a. According to the product rule, we add the exponents, giving us m to the power of a minus a. This simplifies to m to the power of 0, which we already proved equals 1. Because their product is 1, m to the power of negative a is the reciprocal of m to the power of a. Thus, m to the power of negative a equals 1 divided by m to the power of a. Let's put your knowledge to the test with another practice problem. Evaluate and simplify the following expression, m to the negative third power multiplied by m to the power of 0, and then multiplied by m to the fifth power. Think about how to combine these different exponent types. Let's solve this efficiently. We can approach this in two ways. First, remember that m to the power of 0 equals 1. Multiplying by 1 doesn't change anything, so we can focus on the remaining terms. Now, apply the product rule by adding the exponents, negative 3 and 5. Negative 3 plus 5 equals 2. This gives us our final simplified result, m squared. Rule number 7 introduces fractional powers. Taking a root can be written using a fraction in the exponent. To understand why, remember the definition of the nth root of a. By definition, the nth root of a is a number that, when raised to the nth power, becomes exactly a. Keep this fundamental relationship in mind as we begin our proof. Now, let's mathematically prove why these two expressions are equal. Let's assume the nth root of a can be written as a to the power of an unknown variable, x. To solve for x, we raise both sides of the equation to the nth power. On the left side, the nth power cancels the root, leaving just a, or a to the first power. On the right side, applying the power to a power rule, we multiply the exponents, getting a to the nx power. Since the bases are identical, their exponents must be equal. Therefore, 1 equals n times x. Dividing both sides by n, we find that x must equal 1 over n. This perfectly proves that the nth root of a is exactly equal to a to the 1 over n power. Let's practice what we just learned with a real problem. Simplify the following expression, the cube root of 8 raised to the second power. Think about how to rewrite the cube root into a fractional power form first. Let's break it down together. First, we know that the number 8 can be written as 2 cubed. Next, rewrite the cube root using a fractional power. The cube root becomes a power of 1 over 3. By applying the power to a power rule, we multiply the inner exponents, 3 times 1 over 3. They cancel out completely, leaving just 2 inside the parentheses. Finally, we square that result. 2 to the second power equals 4. So, our final answer is 4. Another name for the root sign is the radical sign. The square root of p is written with this symbol, and multiplying it by itself gives us p. In the expression of the nth root of p, the symbol itself is called the radical sign, and the value inside, p, is called the radicand. This radical sign always represents the non-negative root when multiple roots exist. For any real number p greater than 0, squaring either r or negative r results in p. Here, the positive result, r, is called the principal square root of p. On the other hand, the negative result, negative r, is called the minor square root of p. Remember that the radical symbol by itself always denotes the principal, non-negative root. Let's check your understanding with a comprehensive problem. Identify the radicand of the expression, the fourth root of 16. Then, find both its principal square root and its minor square root. Let's break down the solution. First, the value inside the radical sign is 16, so the radicand is 16. Next, we look for a number that equals 16 when multiplied 4 times, which is 2. Therefore, the positive result, 2, is the principal square root, and the negative result, negative 2, is the minor square root. Both values satisfy the core definition of the radical relationship. In practice, this means that every positive number always has 2 square roots. One is a positive value, which we call the principal square root. The other is a negative value, known as the minor square root. Squaring either of these 2 roots will always result in the original positive number. Let's look at this concept through a mirror reflection analogy. Imagine a target number inside a special room. Both a real object and its opposite reflection in the mirror cast the exact same shadow when squared. The squaring process acts like a filter that hides the original sign, revealing 2 opposite paths leading back to a single source. Now, let's look at a practice quiz to test your skills. Find both square roots of 49 and clearly state which one is the minor root. Think about how the dual nature of roots applies to this positive integer value. Let's break down the solution step by step. We know that 7 squared equals 49, making positive 7 the principal square root. At the same time, negative 7 squared also equals 49. Therefore, negative 7 is the minor square root. The final answers are positive 7 and negative 7. Let's explore the multiplicative property of square roots. The property states that the square root of mc is exactly equal to the square root of m multiplied by the square root of c. This rule allows us to simplify complex radical expressions by factoring the radicand first. Now, let's mathematically prove why this property holds true. First, remember that any square root can be rewritten as a fractional power of 1 over 2. Therefore, the square root of mc becomes the expression mc raised to the half power. According to the laws of exponents, we can distribute this power of 1 over 2 to each factor inside. This gives us m to the half power, multiplied by c to the half power. Finally, convert these fractional exponents back into radical signs. This beautifully results in the square root of m times the square root of c, completing our proof. A factor of a number is a number that divides into it without a remainder. For example, 1, 2, 3, 6, 9, and 18 are factors of 18. To factor a number means to write it as a product of its factors, such as 18 equals 9 times 2. Factoring is an essential step when simplifying square roots. Now let's solve a practice problem using this concept. Let's simplify the square root of 18. First, we split 18 into its factors, choosing a perfect square, 9 times 2. Next, we split the radical into the square root of 9 multiplied by the square root of 2. Since the square root of 9 simplifies perfectly to 3, our final simplified answer is 3 times the square root of 2. Let's mathematically prove the division property of square roots. Any square root can be expressed as a fractional power of 1 over 2. Therefore, the square root of m over c can be written as the fraction m over c raised to the half power. According to the rules of exponents, we distribute the power of 1 over 2 to both the numerator and the denominator. This gives us m to the half power over c to the half power. Finally, converting these fractional exponents back into radical symbols, we neatly get the square root of m divided by the square root of c. Now let's apply this property to a practice quiz. Let's simplify the square root of 3 over 16. First, according to our division property, we split the radical into the numerator and the denominator. This gives us the square root of 3 divided by the square root of 16. Since 16 is a perfect square, its square root simplifies perfectly to 4. Therefore, our final simplified answer is the square root of 3 over 4. A fraction is any number expressed as one integer divided by another integer. Fractions are written in the form of p over q, where p and q are integers and q cannot be 0. The top number, p, is called the numerator, and the bottom number, q, is called the denominator. A fraction with a denominator of 0 is undefined because you cannot divide by 0. Equivalent fractions are fractions that express the exact same value. For example, 3 over 4 is equal to 6 over 8, and 1 over 3 has the same value as 3 over 9. To simplify 6 over 8 to 3 over 4, you can rewrite the numerator and denominator as products of factors. Then, you can cancel out the common factor, 2, by dividing both parts to produce the equivalent irreducible fraction. Let's check your skills with a practice quiz. Simplify the given fraction, 12 over 15, into its simplest equivalent form. Think about finding the greatest common factor for both the numerator and the denominator. Let's solve this efficiently. First, we find that both 12 and 15 can be divided by their greatest common factor, which is 3. We rewrite 12 as 4 times 3 and 15 as 5 times 3. By canceling out the common factor of 3 from both the top and the bottom, we produce the final simplified equivalent fraction for over 5. To multiply two fractions, we find the product of the numerators and divide that by the product of the denominators. In other words, simply multiply the top numbers together and multiply the bottom numbers together. Now let's look at a practice quiz. Let's multiply 2 over 3 by 5 over 7. First, we find the product of the numerators by multiplying 2 and 5, which gives us 10. Next, we find the product of the denominators by multiplying 3 and 7, which equals 21. Combining these two parts together, our final simplified answer is 10 over 21. You should always give your answer in its simplest form. With more complicated examples, factor the numerators and denominators and cancel common factors. It will save a lot of time if you do this before you compute the products. Let's practice with a useful example. Multiply 3 over 8 by 4 over 9. Instead of multiplying straight across to get large numbers, let's factor first. Notice that 4 and 8 share a common factor of 4, and 3 and 9 share a common factor of 3. By canceling out these common factors before computing, the expression beautifully reduces. We are left with 1 times 1 on top and 2 times 3 on the bottom. Our final simplified answer is 1 over 6. The reciprocal of a fraction c over d is d over c, since their product equals 1. To divide by a fraction, you simply multiply by its reciprocal. This rule allows us to change any complex fraction division into a simple multiplication task. Let's practice with an example. Divide 2 over 3 by 5 over 4. According to the rule, we change the division into a multiplication by flipping 5 over 4 into its reciprocal for over 5. Now multiply the top numbers, 2 and 4, to get 8. Then multiply the bottom numbers, 3 and 5, to get 15. Our final simplified result is 8 over 15. To find the sum or the difference of two fractions with the same denominator, just add or subtract the numerators, then divide by the common denominator. Keep the bottom number exactly as it is, and only perform the math on the top numbers. Let's think about this using a pizza analogy. The denominator tells you how many slices make up a whole pizza pie. If you have 1 slice out of 8, and add 3 more slices out of the same 8, the size of each slice does not change. You simply have 1 plus 3, which equals 4 slices out of 8 in total. Now let's solve a practice problem. Let's calculate 1 over 7 plus 4 over 7. Since the denominators are both 7, we keep the common denominator fixed on the bottom. Next, we add the numerators on top, 1 plus 4, which gives us 5. Our final simplified answer is 5 over 7. To add fractions with different denominators, we first convert them into equivalent fractions with the same denominator. This common denominator must be the least common multiple, or LCM, of the two denominators. The LCM is the smallest possible number that is perfectly divisible by both numbers. Let's visualize this using chocolate bars with different grid sizes. Imagine one bar split into 2 large pieces and another bar split into 3 medium pieces. You cannot easily add 1/2 and 1/3 because their slice sizes are totally different. To solve this, we draw a new grid, cutting both bars into 6 tiny equal blocks. Now, 1/2 becomes 3 blocks and 1/3 becomes 2 blocks. With the exact same block sizes, we can finally add them together to get 5 blocks out of 6. Let's put your skills to the test with a practice quiz. Calculate and simplify the sum of 1 over 4 and 2 over 3. Remember to find the least common multiple of the denominators first. Let's solve it together. The denominators are 4 and 3, and their least common multiple is 12. We convert 1 over 4 by multiplying the top and bottom by 3, making it 3 over 12. We convert 2 over 3 by multiplying the top and bottom by 4, making it 8 over 12. Now that they share a common denominator, we simply add the numerators, 3 plus 8. This gives us our final answer, 11 over 12.